Our last topic in section 1.5 is even and odd functions. Now, we've already talked about symmetry in our class, right? We talked about symmetry with respect to the x-axis. We talked about symmetry with respect to the y-axis. And we talked about symmetry with respect to the origin. Now, this particular topic is only going to apply to functions. And you might recall that we said functions cannot have x-axis symmetry. The reason being, if a graph has x-axis symmetry, well, then it's not going to pass the vertical line test, which means it can't be a function. So this only has to deal with functions. We are only going to be worried about, in this case, y-axis and origin symmetry. A function is said to be even if its graph is symmetric with respect to the y-axis. Okay, so if it has y-axis symmetry, we are going to call that function an even function. A function is said to be odd if its graph is symmetric with respect to the origin. Now, graphically, you guys should already know what these look like, but let's talk about finding out whether or not a function is even or odd algebraically. To test to see whether a function is even or odd, we are going to evaluate f of negative x and simplify the expression. Again, we are going to plug in a negative x wherever we see an x. I strongly recommend that you put parentheses around all of those quantities and simplify out the expression. What we get when we simplify will tell us whether or not our function is even, odd, or maybe neither in some cases. All right? If the end result is the same as the original function, in other words, plugging in negative x into the function gave out the exact same thing as the original function f of x, the function is even and it will have y-axis symmetry. If the end result is the opposite, that's negative 1 times the original function, f of negative x is equal to negative f of x. This tells me that plugging in negative x, that's what our test is, results in negative 1 times the original function. The function is odd, and therefore it is going to have origin symmetry. Let's go through a couple examples. Determine whether the following function is even, odd, or neither. If the function is even or odd, explain what this means in terms of symmetry. So here we have f of x is equal to x to the 6 minus 2x squared plus 3. Well, how do we test to determine whether or not a function is even, odd, or neither? We need to evaluate f of negative x. F of negative x is equal to negative x to the 6th minus 2 times negative x squared plus 3. Notice, for every single value of x, I substituted in a negative x. It is important to recognize that whenever you raise a negative quantity to an even exponent, that value will always end up being positive. Notice here I have negative x raised to the 6th power. Our goal now is to simplify this expression. When I simplify this, that is going to give me a positive x to the 6th power. Here, I have a negative x squared. Again, raising any negative to an even exponent will make that entire quantity positive. So I still have a negative 2 times a positive x squared. Simplifying this down gives me x to the 6th power minus 2x squared plus 3. Now that we have fully simplified it, let's compare this to the original expression. We notice that they are exactly the same. In other words, f of negative x, evaluating f of negative x, plugging in a negative x, resulted in the exact same thing as if we were to evaluate f of x. It resulted in the exact same thing as the original function. If we end up with the exact same thing as the original, this means that our function is even, and that means it has y-axis symmetry. We could check our work using a graphing calculator. Plugging this function into the calculator and graphing it would give us a curve that looks like this. Notice, if we were to reflect this graph over the y-axis, we would end up with the exact same image. Let's try another one. Determine whether the following function is even, odd, or neither. If the function is even or odd, explain what this means in terms of symmetry. Well, again, the test is exactly the same. We need to evaluate f of negative x. That means we are going to plug in a negative x everywhere we see an x. F of negative x is equal to negative x cubed minus 3 times negative x plus 1. Again, guys, when you guys are evaluating, put everything that you're plugging in inside of parentheses. It will make your life so much easier. Now we need to simplify. Well, here I have a negative quantity that is being cubed. Whenever you go to cube a negative, the end result is still going to be negative. Therefore, negative x to the third still gives us negative x to the third. Here I have a negative 3 times a negative 3x. When I multiply a negative times a negative, that is going to become a positive. Simplifying down results in a negative x cubed plus 3x plus 1. Let's compare that to the original expression. Well, after simplifying, we can see that the expression is not the same as the original. That is definitely not the same thing as x cubed minus 3x plus 1. And it is not the opposite of the original either. Yes, this x cubed term is the opposite. This 3x term is the opposite of negative 3x, but the plus 1 is exactly the same. In order for this function, in order for our end result to be the opposite, negative 1 times f of x, all of the signs would have to be flipped. In this case, they are not. Therefore, because it's not the same and it's not the opposite, it is neither. This function does not have origin symmetry or y-axis symmetry. And we could graph that function and recognize, yes, it doesn't have y-axis symmetry and it doesn't have origin symmetry either. Determine whether the following function is even, odd, or neither. If the function is even or odd, explain what this means in terms of symmetry. How do we do our test? Evaluate f of negative x. Substitute a negative x in for every single one of our x's. F of negative x is equal to negative x times the square root of 1 minus a negative x squared. Now we need to simplify. Is anything going to simplify here? Well, here I have a negative quantity being squared. As we talked about earlier, anytime I raise a negative quantity to an even exponent, that is going to become a positive. All right, so this is going to become a 1 minus an x squared, again, inside of my parentheses, or inside of my square root. This gives me negative x times the square root of 1 minus x squared. Let's now compare this to our original expression, our original equation for f of x. Is it exactly the same? No. What's different? I am actually taking the original and I am multiplying it by negative 1. That means that they are opposites of each other. After simplifying, we are left with the opposite of the original function. F of negative x gave us negative 1 times the original function f of x. This is negative 1 times x root 1 minus x squared. Notice that's the exact same thing as the original. So, because it is the opposite, that means that our function is odd, and odd means that it has origin symmetry. Again, if we were to graph this in our calculator, this is the shape of our graph. If we take that graph and we reflect it over the x-axis and the y-axis, we end up with the exact same image. All right, one more here. Determine whether the following function is even, odd, or neither. If the function is even or odd, explain what this means in terms of symmetry. To test, we need to evaluate h of negative x. Plug in negative x wherever we see an x. H of negative x is equal to 1 divided by the quantity negative x cubed minus negative x. Well, here, again, we have a negative that is being cubed. Anytime I raise a negative to an odd exponent, that value will still stay negative. This will simplify into negative x cubed. Here, I am subtracting a negative x. Subtracting a negative x turns into adding x, leaving me with 1 divided by negative x cubed plus x. Let's compare this to the original expression. Well, take a look. Is it exactly the same as the original? No, it is not. Is it the opposite of the original? This is a little bit trickier to tell, but it actually is. Okay, this is the opposite of the original. All right. One thing to recognize is that when you are dealing with fractions, to get the opposite of a fraction, you can multiply it by -1. And it doesn't matter if that negative goes into the numerator or if it goes into the denominator. Right? If I have a -1 divided by 2, that's the exact same thing as 1 divided by -2. I could have the negative up top or the negative in the bottom. Notice that if we multiply the denominator of our original expression by -1, we see what we have right here, negative x cubed plus x. Because of that relationship, we find that h of negative x actually gives us the opposite of our original. Okay, after simplifying, we are left with the opposite of the original function. H of negative x is equal to -1 times h of x, meaning it is odd, and that we have origin symmetry. Graphically, we could check our work. Okay, all right, notice here that I actually have just factored out a -1. If I factor out a -1 from each one of these terms and bring it to the front, this is -1 times 1 over x cubed minus x. That's -1 times the original function. And graphically, if we were to plot this in our calculator, we end up with this nice looking curve right here, which does have origin symmetry. If I reflect that graph over the x-axis and the y-axis, I end up with the exact same image. All right, there we have it, even and odd functions.